the real stuff, because there's not just one ion, right? But let's imagine we have a cell, in this case a neuron. We'll focus on the axon because this is where things are going to take place, and we're going to focus on not on everything in the axon, but actually very close to the membrane. And in this case, we'll just have a cell with a potassium. We can actually do that in the lab. We can make artificial cell or just put a cell just with potassium, but we don't need a lab here. So light blue, ECF, extracellular fluid. The brownish part is the cytosol. And as you can see, I put a bigger font for the K. We have a higher concentration to begin with in the cytosol compared to the outside. Okay, that's where we begin. How exactly this happens, we'll talk about it later, but that's a given. So you guys will help me. We don't need to raise your hands. I'm going to count to 3 before we answer the next question, and we'll ask them as a class. Chemically wise, just chemically, okay, will the chemical gradient drive potassium in or out? Think about it for a little bit. We're going to count to 3 and just say what you think. 1, 2, 3. Wonderful. Higher to lower. Always works like that. Okay. So potassium wants to leave, right? It has leak channels, so it can leave. It has that broken window that it can leave through. So potassium will start leaving. That's basically the idea. If we zoom in, here's the membrane. In yellow now is the cytosol. Here's the potassium leak channel, and the purple balls or circles are going, these are representing potassium. Potassium is going to start leaving. Now what you see here, so potassium leaves the cell via potassium leak channels to the chemical gradient. That's pretty obvious. In blue, what you see here are proteins. Most of the proteins are more negatively charged than positively charged, so they provide us most of the negative charge. Now, before potassium started to leave, everything was in balance electrically, plus and minuses inside the cell. As potassium leaves, we're losing 1 ion of potassium. That means we're losing a positive charge in the back, right, where we just left, at home. So as we are, I will just use very simplified terms, not physics here. Potassium wants to, right? It doesn't really want anything, but it wants to leave to solve the gradient, right? And it's not going to be just 1 ion, it's going to be more than that. But as if I'm a potassium ion right now in the cytosol, and as I'm leaving the cell to solve that gradient, to equalize everything, what type of imbalance of gradient do I create in the back at home? An electrical gradient. Everything was perfect, pluses, minuses. I just lost 1. I just lost an ion. So as potassium leaves to solve the chemical gradient, we are starting to build up an electrical gradient. And the more potassium will leave to solve the chemical gradient will be gradually going kind of to solve it, right? To equalize everything, we are building a greater and greater electrical gradient. So negatively charged proteins cannot leave the cells, and that would balance everything, but they cannot. You don't have the leak channels. So what we do is potassium is leaving, and electrical gradient starts to pick up. That gradient is now telling potassium, come back home, there's a mess here. You just left to solve the chemical gradient. We're here with an electrical problem. So ions of potassium at a given state will leave, but some will come back. Okay? Now, we're going to start using the word membrane potential right now. Whenever I say membrane potential, it's always electrical membrane potential in voltage. Okay? Another consensus that we use, whenever we talk about the membrane potential, we measure potential inside compared to the outside. Again, we put an electrode inside a cell to measure, and we compare the potential compared to the outside. So when we say that a membrane potential will be positive, it doesn't mean that it just has cation. It just means that it's more positive than the potential in the ECF, okay? So knowing that, talk with each other. Well, I believe you'll get that, but let's just make sure we get it. So I can just guess that those that did not answer negative are those who took with me 202. You know that whatever seems straightforward is probably the opposite, but it's not always like that. No, this is true, right? What's the rationale? Those who suggested negative and you were correct. Why did you choose negative? Help me. Come on. Yeah.
So as we know, the positive charge is attracted to the negative charge. So as the potassium ions leave, you have a buildup of negative charge inside
Wonderful.
the cell. So the potassium ions are going to be attracted
Wonderful.
to that negative.
I know we have an outflow of potassium, right? Potassium is a plus, it's a cation. We're talking about a potential that drives it back in, it has to be negative. Pluses do not like pluses, pluses are attracted to minuses and vice versa. Make sense? Okay. So this is how we begin, and then the potassium will leave and will leave because of the chemical gradient. The more it leaves, the more electrical gradient is still building up. To begin with, the chemical, it's kind of like a tug of war, right? Chemical versus electrical. And in the beginning, the chemical will still win. Ions will leave and ions will come back, but more ions will leave than come back. But the more they leave, the greater the electrical potential, right? And the lower becomes the chemical potential. At some point, enough potassium ions will leave. Okay, again, I'm potassium. I'm now leaving, and all my bodies are leaving with me. And at some point, the electrical potential that attracts me back to the cell is so strong that it cancels out. It completely counteracts and cancels out the chemical gradient, basically. So as a result, the chemical pools from here, the electrical pools from here, at some point will reach a net flow of 0. It's not that we have 0 movement, we have a net flow of 0. There will be just as many ions of potassium leaving as we have of potassium entering, and that specific membrane potential is what we call GRQ, the reversal potential. The reversal potential of a given ion is the membrane potential at which the net flow of the ions across the membrane would be 0. Add S to the ion. Yes? Emma. Wonderful question. Emma is asking, how is that different from the resting potential? So the reversal potential is a property of a given ion at a specific condition. What was the condition we discussed? We said potassium, nothing else. Reversal potential does not take into account all the other ions. It takes into account basically one thing, a bit more than one thing, but one thing mainly. And that's a given ion and the concentrations of that ion outside compared to the inside. Okay? In most of the cells, what we saw is pretty representing. It's not just in the axon, but we have cells in our inner ear, for example. We have cells where we have more potassium outside compared to the inside. The reversal potential will be different at that point. Okay? There are other factors like temperature, but these are not factors that really change in our physiological conditions. So again, our reversal potential is not telling us what's happening right now in the resting state. It tells us a property of a given ion. It's completely independent of what happens with sodium and chloride and anything else, or proteins, whatever. Just that property, assuming, of course, that potassium can also leave and go and in and out. Okay? I put it here. I don't know if you can see that. I'll just say that aloud. We have two other names for that if you see them. Reversal potential is one. We also have equilibrium potential because the cells reach equilibrium. You can think about reversal, by the way, as the electrical potential just reversed the flow of the ion. And we have Nernst potential, another name. After Nernst, we're actually the one that discovered, and there's a Nernst equation. Anyone? Physics? You learned about the Nernst equation? Right, so some of you are familiar. We're not going to go to the levels of the Nernst equation, but that's putting the temperature, the concentration, all of this into a physical equation. I will send you an email maybe today, maybe tomorrow. I want to encourage you to do something. It's not mandatory, you don't have to do it, but one of our faculty members, together with someone else, developed some sort of an app, like a training app, and they developed it around this topic and about ions moving in and out. And they are going to develop something about action potential. I will send you a link, and it's also going to be in the library. And I will actually encourage you to go and check to see and let me know whether it was helpful, not helpful, who knows? Okay? Okay, so I'll answer more questions about reversal potential if you have, but let's start to ask the what if question. Things apply, okay? So we talked about potassium, you guys now will do the analysis of sodium. So sodium is found in higher levels on the outside compared to the inside. The question is, what about sodium? What will be the reversal potential of sodium in this specific cell? It can be 0, it can be positive, it can be negative. Try to do it by yourself after I'm delivering the learning catalytics, and once you're done, start. Why positive?
So when the chemical gradient of sodium both go inside the cell, so outside the cell is negative. So when you have a positive cell, they'll both be positive and negative.
Okay, so what Rob said, tell me if I'm saying it correctly. The flow, the chemical, we're saying we all agree it's going in, right? High concentration outside. Flipped image of what we discussed about potassium, right? The way I ask this, it might be a bit different than what you said, but the way I ask this is, okay, what type of electrical membrane potential will counterbalance, will throw sodium out, right? Sodium is plus or minus. It's a plus. What type of membrane potential throws pluses out of the cell? Plus. They don't like plus, they don't like each other, right? Perfect. The answer is indeed positive, and it's about plus 30 millivolts. You need to remember the numbers. Okay, and this is not always intuitive. It can be something sometimes counterintuitive. Again, think about this as a given ion, regardless of what happens outside of the cell. What's the reversal potential of potassium? You know the numbers, you did the GRQ, negative 88, right? Sodium, about plus 30. So now we talked about reversal potentials. Maybe, first of all, do you have any other questions, more questions about reversal potential? Yes? Yeah, that's a difficult concept, yeah. Again, I'll repeat the reversal about the reversal potential. First of all, remember, it's not the resting potential, it's a property. Just like you have a charge for an ion or a given concentration. It's a property of a membrane with regards to a specific ion based on the initial concentration, outside and inside. Okay? The reversal potential tells us what will be the potential that at that potential we will have 0 net flow. There will be just as many ions that leave as ions that enter. Because the chemical gradient drives the ions one direction or the other, in this case inside the cell, the membrane potential will be the one that back counteracts it, right? Sends it back outside. Since sodium is a plus, the membrane potential has to be a plus, because plus do not like plus. Okay? You have a question?
Yeah, are there any situations where the reversal potential would be 0?
Would the reversal potential be 0? Depends. I mean, I don't know the physiological conditions right now, but it depends on the concentrations. Okay? So for example, if you had an equal concentration of a given ion, let's say sodium, but that cell has exactly the same concentrations inside and outside. It doesn't happen in reality, but let's say, what will be the flow of, what will be the chemical gradient, what will be the flow, outside or inside? Same concentrations. 0, right? They will not go anywhere because they don't want to go. There's no driving force. How can we cancel out a 0? We'll have a 0 millivolt. Yes? Okay, so it's not, the question was, because we have accumulation, there's a negative inside. Don't think about it this way. I completely understand your line of thinking. Think about it just simply as what will drive the ion back into its original location, okay? Maybe I'll address your line of thinking, which is completely correct, but I'll explain why it can be problematic and can confuse you, but later on. Yes, last question about this.
I know resting membrane potentials can be given a number like -70 millivolts. Can these also be quantified?
Yeah, so this is plus 30 millivolts in a normal average, let's say, neon. Yeah, it will be a number, exactly. It can be experimentally done. Okay, and again, it's not, this is the Nernst equation, basically. When you put concentrations, it's a logarithmic equation, and you get a number at the end. No need to know the equation itself. Okay, let's start to talk about the resting. We talked about reversal, but not really. The real life event is a membrane with not just sodium, but also potassium. There are also other ions, but these are the two ions that will be the main players in this game. Okay? So if you think about it, the resting membrane potential should be somewhat of an average, right, of the mean between those two reversals. It's a combination, merging of those two membrane potentials. Potassium on one hand, and sodium on the other hand. But the answer is a bit different, actually. The resting membrane potential, let's see, I said negative 88 for potassium reversal, and I said plus 30 for sodium. Now you guys probably know what's the number for a typical cell for the resting membrane potential. It's negative 70 millivolts, right? So negative 70 is not exactly negative 30, plus 30 and negative 88, right? It's much closer to potassium. So what's going on here? What is the resting membrane potential? The resting membrane potential does indeed entail all the reversal potentials, in this case sodium and potassium mainly. But there's one other factor that kicks in, which we did not address until now. When I discussed the reversal potential, I said imagine you have a membrane and that membrane is permeable. It's not just a driving force, the potassium can get in and out, the sodium can get in and out. Resting potential tells you the story, the real story. And in the real story, permeability of the membrane is not identical when it comes to the different ions. It's much harder for sodium to get in compared to how much potassium can leave. Why? Because of the concentrations of leak channels, exactly. So the sodium impact on the membrane potential is much lower than the potassium, since the membrane is much less permeable to sodium. It's not completely impermeable. There are leak channels for sodium, but not at the same level, not at the same scale as we have for potassium. Therefore, potassium is the key player, is the leading player in this game that determines the resting membrane potential. Now, it's not negative 88 because we still have sodium, so it pushes it a little bit down, and it's negative 70 millivolts. If you're more of a visual learner like myself, you can just imagine our classroom. Our classroom is going to be a cell right now. Think that we're all in a cell, okay? And we have doors that are, or windows, broken windows that are for some of the students, those that have blonde hair. And we have some doors for those who only have black hair. But we only have 2 doors for those that have blonde hair. And we have 400 doors for those who have black hair. So it's not the same. If they want to move in or out, right, it's going to be a different effect, a different impact. So that's going to be the resting membrane potential, which is about negative 70 millivolts, depending on the exact cell, but typically in a regular neuron, a regular axon, that's the case. And of course, it's negative. Everything that I said now, it looks like we are talking about tons and tons and tons and tons of ions that move. Actually, not many. There are very few of them relative to the number of ions. Okay? So, before that, we'll talk about that. But before that, maybe, or any question? Oh, sorry, you had a question.
Yeah, why is the potential negative?
Because potassium, remember we said the reversal membrane potential of potassium is negative, right? It's negative 88. And since potassium has a greater impact because it actually can move, while sodium theoretically wants to move but cannot really move so much, okay? So potassium will have a greater impact on the membrane potential, and the membrane potential will be much closer to negative 88. That's why it's negative. It's not because we count the number of ions of potassium comparing it to the ions of sodium. There are a lot of other ions over there. There are the charged proteins negatively and positively. That's not the story here. I started the first question asking you, telling you sodium or potassium was higher inside and lower outside. Again, I asked you this, but I'll just ask you again, what would have happened if we had an equal number of ions of potassium in both sides? Will they move anywhere? No, we won't have any membrane potential, right, if we had it for potassium. So in order for them to move, in order for them to create a membrane potential, we need to start with that chemical gradient. I told you there's a chemical gradient. How do we reach the chemical gradient to begin with, though? Anyone wants to suggest? You read a bit about that. I'm talking about the hardest working protein in your body. The sodium-potassium pump. We're going to come back to the sodium-potassium pump more than you can ever imagine in this class. It's really one of the hardest working, if not the hardest working proteins in your body. Involved not just in establishing the membrane potential, but it's one of the main things. And it's all working not just in neurons. Each and every cell has a resting membrane potential. So what we have, we create that gradient with the sodium-potassium pump that throws sodium outside and has potassium inside. So the pump restores the chemical gradient and therefore maintains the resting membrane potential. And so there are two things that the pump is doing here. First of all, it starts the chemical gradient to begin with, right? Otherwise we won't have a flow. But now imagine that once it's created the chemical gradient, we would have just thrown it out. We said that sodium is not so permeable, right? Membrane is not so permeable to sodium, but it's still permeable. So if we just wait enough time, then eventually sodium will balance itself and potassium will balance itself and everybody will be happy, and we will not be happy because we need that gradient. So remember that few doors for the blonde students, right? And many doors for the black-haired student, right, that wanted to leave. Now, you have those students, remember, imagine that there are students outside. I mean, imagine last week in physiology. Remember that? You had many, many students who tried to get into the class. Now, imagine that I would just have 2 doors for them, right? They will try to get in. But now imagine that in addition to that, there's a guy here, like a doorman, right, sitting next to a club and making sure whoever came in, boom, and catching them and throwing them outside. So it's not just the issue of that it's not so permeable, but even those that get in, they've been thrown outside. And as a result, we make sure that we have a gradient to begin with, and after that, to maintain a gradient. When we will learn later on about the action potential, we will see that we are changing the game here. Ions are going to move in and out, a lot of mess. The sodium-potassium pump will help us go back and establish again the original concentration gradient. Okay, and this is what I was referring to, 0.006%. So look at the numbers of the potassium actually move. You don't need a lot of movement to create that change inside the cell. It's all logarithmic, that's why we have an impact. A great impact with just a little bit of movement. Any questions about the reversal membrane potential and about the resting membrane potential? And please note, just what will happen in many cases in this class, if you are now sitting and you have no idea what I'm talking about, don't freak out about this. You are fine. You are one of hundreds who took this class. Sometimes we just need to process it after that. So after the class, today, tomorrow, whenever, go back, listen to me, record, go back to the slide and process and make sure and start to ask yourself questions. Okay? Remember the what-if questions. Think about chloride. I'll just tell you, we have more chloride outside compared to the inside. You'll think, not here. What's the reversal potential for chloride? Yes, Sarah?
Is that the percentage of potassium that moves due to the pump or due to the leak?
No, this is the percentage that moves just through the leak channels, basically. Any questions? So that's our resting state. Let's summarize this. The membrane, and if I don't see you, just shout. I'm trying to see if someone is raising their hand, but I might miss that, so just give me a shout here. The membrane is much more permeable to potassium compared to sodium. The electrical gradient counteracts the chemical gradient, and the ions reach eventually equilibrium or the nurse potential. And the sodium-potassium pump maintains the chemical gradient and is essential to create as well as to maintain a negative resting membrane potential in that cell. This was resting. We did not stimulate, we did not change anything. We just worked with the leak channels and with the concentrations that we had. Okay? So we basically covered to explain what determines and maintains the membrane potential, and we started to talk about different ion channels, but we just talked about the leak channels, and now we're going to make some changes. And before we make changes, we need to introduce us to the other channels that you read about, but this time I am going to go a bit into your sign reading just to make sure we are familiar with this. So I mentioned last time we have 4 types of channels that we can divide into 2 groups: non-gated, aka leak channels, and gated. And when we talk about the gated channels, these are channels that can be open or closed based on a stimulus. Now we talk about 3 groups of channels. The first ones that we're going to address are the chemically or the ligand-gated channels. Some would pronounce it ligand. I'm using ligand, but whatever works for you. These are seen here in purple, and each channel in this case is composed of 2 proteins. Now, please, I think you know this, but any diagram that I'm going to show here has nothing to do with what it really looks like, okay? It's all 3-dimensional. We just use it for simplicity. And by the way, nothing is really still, and that's also important to remember, okay? When we see an ion, and now the channel opens up, no, it's all crazy movie. Everything is moving everywhere. So in this case, again, cytosol in yellow, and the ECF is outside. We see which type of ions you'll tell me what ions these are, just based on where they are and how they're going to flow in. Potassium or sodium, between the two. These are sodium ions, right? They're outside in higher concentration. If we allow them, they will move in. Now remember, sodium wants to go in. It always wants to go in. But it cannot do such a great job because it doesn't have a lot of leak channels. And even if it makes it, the sodium-potassium pump throws it out. But now we can open new channels. And these specific ones are ligand-gated sodium channels. Now the ligand is the red dot that you see here. They have their own specific configuration. It's a 3-dimensional conformation or configuration. And at a given state, they're closed. Okay? If I'm a ligand, if I'm a gated channel, let's say this is me, this is closed. Okay? I'm like that. But if someone comes and shakes my hand, then that will change something, right? That will change my structure. Amino acids, attraction, non-attraction, and I'm going to change my conformation. And that change in conformation will be my opening for ions to move through me. So does this mean that any ligand will go and bind to the ligand-gated channel? No, and I gave you an example of epinephrine versus acetylcholine, right? No, we have specificity. Typically, it's not a specificity only for one specific ligand. We'll have a few ligands that can bind. We call them analogs or not, but we're going to talk about one specific ligand. So this is an example of the most famous ligand-gated channel, the acetylcholine sodium channel. What you see here is sodium will be purple outside, wants to get in, no channels. But acetylcholine, which is acetylcholine, will bind to specific sites on the channel, will change its configuration, it opens up, and once it opens up, sodium can get in. Now, you can see only sodium. I actually wrote in parentheses, this is not true. One of those misconceptions. Actually, acetylcholine ligand-gated channel can allow potassium to leave as well. We will not discuss it, we will completely ignore it, just for the sake of not confusing us even more, okay? Because I will just say that the impact of sodium will flow in more than potassium will leave, okay? But we'll leave it as that. You'll just have to trust me. So we are going to stick to the name sodium ligand-gated channel. So we have 2 levels of specificity, right? One is for the ligand. It's an acetylcholine ligand-gated channel. It's not an epinephrine. And the second level of specificity is to can chloride go in? Nope. It's to the ion. Any questions about ligand-gated channels? Yep. They will not play a role in maintaining the resting membrane potential because the resting membrane potential does not involve any gated channels. Okay, it's only leak channels and the sodium-potassium pump. That's the only thing. They will mess up with the resting membrane potential and create another potential that we need to maintain after that. Okay? I had another one raising the hand, I think. So, yeah.
Is there a reason that, I don't know, like, why would it not be advantageous to just have like a pump where sodium combined and then allow sodium to like flow through? Why use two different chemicals?
Why wouldn't it be sodium? Because sodium is always at a time. The question, if I understand correctly, is why wouldn't we just have a sodium-gated sodium channel, right? Sodium needs to go in, it will just open a channel. Because then all the channels will open up. Because sodium is always in higher concentration outside. We don't want it to go in. We want it to go in when we say that, when we tell it to go in. How do we tell it to go in? We're going to secrete a ligand that will bind to the receptor. Otherwise, it will behave just like a leak channel. We don't want that. Yes?
Are ligands typically negative?
No, the ligand is not negative. A ligand is a
protein.
molecule. It can be a protein, it can be something else, typically a protein or short amino acids. Many neurotransmitters, we'll talk about them later on. No, not an ion. Excellent. Okay, ligand-gated channels are one. The second group are called voltage-gated channels. They can also open or close, but this time the stimulus is not a molecule that binds to them, but it's a voltage. How can voltage, again, now I'm a voltage-gated channel. I change my configuration. I'm like this now, okay? Something happens, as a result, I'm now doing this. And now I'm open. And back into closed. How can voltage affect me? Anyone has any idea? How would voltage serve as a stimulus? Voltage are charges, right? How by changing the voltage? Right.
Voltage is product of charge that's created. So the protein is
Wonderful. The channel is a protein, right? Hear me again. Here I am, right? My fingers are amino acids, residues, right? And I'm all full of amino acids. And you know amino acids, basically, sometimes they're positively charged, sometimes they're negatively, sometimes they're not, sometimes they're just polarized. So if I change the charge around them, that will change the angle, and that will change my conformation, my configuration. So this is voltage-gated channels. They are responding to a stimulus. We'll talk a lot about them on Thursday when we talk about the action potential. I already want to mention that the fact that sometimes, in this case, these are two gates in the same channel. Gates can open or close, but not necessarily at the same speed. This sounds like just a small anecdotal fact, but every morning when you wake up, before you have your cup of coffee, please thank evolution for that small thing about different speeds, because that's what allows you to live, eat, walk, breathe, anything. If we did not have this, if they all open up and close down at the same speed, we will not have this class. So we'll see why when we talk about the action potential on Thursday. Okay, just remember that gates can respond, but think about heavy wooden doors that open up very slowly versus a door that opens like that, or closes like that, And the last group, a group that I mentioned in the GRQ when I asked you about the years, these are the mechanical gated channels. Okay, they are channels that open up mechanically. Basically, if I'm now touching the podium right here, okay, what I have are channels. They are receptors, but they serve as, molecularly, they are channels that are open up physically because I bent my finger, and as a result, they will allow a stream of ions to move in or out, depending, of course, on the ions themselves. It's going to be in this case, mechanically gated channels. Any questions about any of our channels? You read about carrier-mediated, transporter, etc. This is what I'm not going to address again. I just make sure, because it's the beginning of the semester, if you're not sure what you're responsible for, I might ask also about carriers, that the emphasis will be on what we discuss here. Okay, assigned readings, know your GRQs, you're good. Okay, now the membrane, as we said, is negative, the membrane potential, right? It's negative 70 millivolts. We can also use the word polarized, polarized in the sense that it's not zero. Anything that is not zero is polarized. Now, this was resting state, but we actually can change things and we can make it less or more polarized. Depolarization is the process in which we are making the cell less polarized, and hyperpolarization is making the cell more polarized. If I'm taking the cell and change it never mind how, we make it into a negative 95. Is that hyperpolarization or depolarization? This is hyperpolarization. I made it even further from 0. Okay? Now, depolarization, does it mean that I'm making it positive? No, it might. So, how do we do that? We'll focus on depolarization. I'll let you suggest mechanism for hyper later on. So we focus on depolarization. We need to provide a stimulus. If it's going to be a mechanical gated channels, what's going to be the stimulus? A mechanical, physical stimulus, right? Bending of fluid moving through the hairs of the cells in our inner ear, which basically bend them, and as a result, they open channels. That's the way we hear. If it's a ligand, what will be the stimulus? Ligand, very simple, exactly. So we'll give an example of a ligand, but it's just an example. It could have been, let's say, mechanical, okay? So we're going to use an example of the chemical stimulus, and let's zoom out and see the cell, and here is, we'll focus on this part, the dendrites, and here is zooming in, resting membrane state, right? Negative, positive. Please note, I said it last time, but now we should know more about this. It does not mean, you'll tell me, do we have cations in the cytosol? Can you give me a name of a cation? Potassium, we have tons of potassium, right? It's not really just n ions inside, it just means it's to symbolize the fact that it's more negative compared to the outside. That's the reason we put minuses over there. It's a bit confusing, just remember that. We have tons of sodium here in purple that who really wants to get in, because that's a driving force. But again, very few leak channels, and we have a sodium-potassium pump. Now let's make some changes. How would you open these gates? If it's the example that we used 2 slides ago, what would you provide the cell with? A ligand like acetylcholine, right? So let's give this cell acetylcholine. These are the red dots. They will bind to whatever site they have, the binding site. Again, specificity. In order for a molecule to bind to another molecule, it will not stay bound. In order for it to stay bound, we need to have the right conformation of both molecules, both the ligand and in this case, the ligand channel. And remember, we didn't discuss this, but it's not going to stay forever. It's going to close down. So it's a very short period of time when things need to happen. So sodium, now you guys will help me. Goes in or out? In or out? In or out? In. Wonderful, right? Chemical gradient pushes it in. Great. So now we have more sodium here. Now we used to have negative 70 millivolts. But now we have more ions. Remember, we don't need a lot of them to make a change, that are pluses, positively charged inside the cell. So we made the cell more, the membrane more positive. It's not really positive, it's just less negative. We changed the negative 70 to negative 65. We are no longer discussing resting membrane potential. It's not resting anymore. What we created is a change. We created a local event, a local change. And if we zoom out, you can see this is the red bar here represent the stimulus. We created this change only in this area. Now again, it's not really plus. It's just less minus than a regular minus. Okay, it doesn't have to be plus. Hush. This